So here we are, and this is the last of the new topics that'll show up on this year's reduced abbreviated AP exam. Coming up, we think pretty soon, May 12th, it's a Tuesday. So here we go. The nice thing about this topic, we've kind of already done it. So we already know the Maclaurin series. I'm just going to put this up here as a review. The Maclaurin polynomial was this thing that looked like this. It was used to approximate a function. So if we have a function that we already know, we can approximate it by using a polynomial, and the polynomial was designed by kind of piecing together three pieces. The first piece was the derivative of the function evaluated at x equals 0. The second piece was a division by the factorial associated with the same number as the derivative. If you're on the second derivative, 2 factorial. Fifth derivative, 5 factorial. And finally, to turn this thing into a polynomial, we multiply by x raised, again, to the same power. So if we're at k equals 2, it's a second derivative, evaluated at 0, 2 factorial, and x to the second. And we worked our way up, getting as many terms as the problem required us to get. So what's new here? Well, what's new here is this idea of the Taylor polynomial. So here's Taylor up here, and the Taylor polynomial is pretty much the same thing that we just said. That's going to approximate the function. It's going to approximate it at 0. But suppose we wanted to approximate the function somewhere else, not at x equals 0, but at some other x value. Let's call it x sub 0. It could be approximating it at 1 or 2 or negative 5 or wherever we choose to do it. We're going to adjust the Maclaurin polynomial, and we're going to call it a Taylor polynomial. It looks like this. And if we notice, things are kind of similar here. The only difference, we're now evaluating it at x sub 0. And so what we end up with here is the same summation, 0 to n, the same set of derivatives, first, second, third, and so on. But now we're evaluating them at a different value of x. We're doing that same x0 here, x minus the value. So if it's 2, it's x minus 2. And every polynomial term will be x minus 2. So things aren't changing very much. And finally, it's the same factorial in the denominator. So things are fairly similar, and I think the best way to do this is to go ahead and look at an example. So here we are. We're going to take a look at finding the fourth degree. So we're going to go out to k equals 4 here, or n equals 4 actually. K is going to go from 0 to 4. Taylor polynomial, which just means we could be evaluating this anywhere. We're doing it at 2. So that means that we're going to be evaluating all of our derivatives at 2, and we're going to be multiplying by a polynomial. All of them are going to be x minus 2 to the power. So here we are in the same kind of table we looked at for the Maclaurin series. We're going to evaluate our derivatives at x equals 2. We're going to divide them by the factorial number wherever we happen to be, and we're going to multiply by x minus 2 because that's where we're evaluating this polynomial, and raise to the same power. When n is 0, we don't have a derivative. We're just looking at the original function. We know what this is. The original function here is natural log of x. Evaluating at x equals 2, we get natural log of 2. We're dividing by 0 factorial. Well, that's just 1. 0 factorial is equal to 1. And we're going to multiply by x minus 2 to the 0 power. And really all you get here when you multiply these three things together is natural log of 2 times 1 times 1. So just natural log of 2. Let's go to the next line. We're now taking the derivative of natural log of x, so that's 1 over x. Evaluated at 2, that's 1 over 2. Dividing by now 1 factorial, that's just 1 again. And multiplying by the polynomial term x minus 2 to the first power. We multiply these together and we get 1/2 x minus 2. We go to the third row, or actually n equals 2. We're taking the derivative of 1 over x,
We know that one. We'll go back and remember it. It's negative 1 over x squared. Evaluating that at x equals 2, negative 1/4, multiplying by 1 over 2 factorial, that's just 2, and then multiplying by x minus 2 squared. We multiply these three together, we get negative 1/8 x minus 2 squared. We come back and pick up the next one. Now we need the derivative of negative 1 over x squared. Well, that's negative x to the minus 2. Derivative would be 2x to the minus 3. So it's 2 over x cubed, positive. Evaluating this at x equals 2 gets us 2 over 8. We'll leave it alone. Multiplying by 1 over 3 factorial. 3 factorial is 6. And then multiplying by x minus 2 cubed. And that gets us, well, this will reduce 1/4. So we get 1/24 x minus 2 to the third power. And finally, the fourth derivative, well, now we need the derivative of 2x to the minus 3. We can come back up here. That's negative 6x to the minus 4. So that's a negative 6 over x to the fourth. Evaluating this at x equals 2, negative 6 over 2 to the fourth is 16. 1 divided by 4 factorial, well, that's 6 times 4 is 24. And then finally, x minus 2 to the fourth power. When we do some reducing here and simplify that out, we get a value of negative 1 over 64 x minus 2 to the fourth power. Looks like we have 5 terms, and when we put them all together, we get this. The approximate value, and this is not of 2, this is simply the approximate value of x, f of x, can be approximated by this polynomial, and I've just taken all of the terms we worked out and just put them all together. And this is the 4th degree Taylor polynomial. It's Taylor because we're evaluating all of our polynomials. They're all x minus 2s. They're not x's. We evaluated all of our functions and derivatives at the value of x equals 2. We recentered everything. Other than that, it's the same thing we did with Maclaurin series. So I'm going to stop this one here, and I'm going to post a second video that's going to have a couple of more examples just to show an extension or two that we're going to look at with these things. So I'll see you on that side. Thank you.